For most of the AI revolution, artificial intelligence has lived behind a screen. We type a question and a chatbot gives us an answer. We describe an image and an AI generates it. We ask for code, music, video, research, or business advice, and everything happens inside a digital environment. But that is starting to change. AI is leaving the screen. It is entering cars, factories, warehouses, hospitals, farms, construction sites, and eventually, our homes. Instead of simply generating words or images, AI is beginning to understand the physical world, move through it, manipulate objects, and make decisions in real time. This is what people mean when they talk about physical AI. And in my opinion, physical AI could become an even bigger technological shift than generative AI. A language model can tell you how to make a cup of coffee. A physical AI system can find the cup, pick it up, place it under the machine, press the correct buttons, avoid spilling the coffee, and bring it to you. That sounds like a small difference, but technically, it is enormous. The digital world is clean and predictable. Computers operate with structured data, fixed interfaces, and clearly defined rules. The physical world is messy, objects move, lighting changes, floors can be wet, people behave unpredictably. A box may be heavier than expected, a door may be partially blocked. A robot may see an object it has never encountered before. To operate successfully in this environment, an AI system needs much more than language ability. It needs perception, spatial awareness, memory, planning, balance, coordination, and the ability to react immediately when something goes wrong. In other words, physical AI needs to connect intelligence with action. A physical AI system normally begins with sensors. Cameras allow it to see, microphones allow it to hear. Force sensors help it understand pressure and contact. LiDAR and radar can help it measure distance and detect objects. Internal sensors tell the machine how its joints, wheels, or mechanical components are moving. The AI then combines all this information to create an understanding of its surroundings. It must recognize objects, estimate their position, understand what can be touched, predict how things might move, and decide what action to take next. Finally, it sends commands to motors, wheels, arms, hands, or other physical components. This entire process must often happen in fractions of a second. That is why physical AI is not simply ChatGPT installed inside a robot. It is a combination of multimodal AI, computer vision, robotics, simulation, control systems, reinforcement learning, edge computing, and specialized hardware. One of the biggest breakthroughs behind physical AI is the development of vision language, action models. Traditional robots are usually programmed for one specific task. An engineer might define the exact movement required to pick up one type of component from one location and place it somewhere else. That works well in a controlled factory, but the robot may fail when the object moves, the environment changes, or a new product appears. Vision language, action models take a different approach. The robot receives visual information from its cameras, understands a human instruction, reasons about the situation, and generates an appropriate physical action. Instead of programming every movement manually, we can potentially tell a robot, pick up the red container, place it on the lower shelf, and avoid the fragile objects. The robot must understand the words, identify the correct container, find a safe path, control its body, and confirm that the task has been completed. Google DeepMind's Gemini robotics research is a major example of this direction. Its robotics models are designed to combine visual understanding, language instructions, spatial reasoning, planning, and physical control. DeepMind has also demonstrated progress in transferring learned behaviors between different robot bodies, which could make it easier to reuse intelligence across multiple machines. This idea is extremely important today. Every robot platform requires a huge amount of specialized engineering. In the future, companies may build foundation models for robotics, in the same way that companies now build foundation models for language. One general robotics model could potentially be adapted to control a humanoid robot, a warehouse arm, a delivery machine, or another autonomous system. The hardware would be different, but parts of the intelligence could be shared. Another major breakthrough is simulation. Training robots directly in the real world is slow, expensive, and sometimes dangerous. If a robot needs millions of attempts to learn a movement, we cannot always allow it to make those attempts inside a real factory. This is where virtual environments and digital twins become essential. Engineers can create a simulated factory, warehouse, road, or home. Inside that virtual world, thousands of robot instances can practice simultaneously. They can drop objects, crash, make mistakes, and explore different strategies without damaging real equipment. The most successful behaviors can then be transferred from simulation to physical machines. NVIDIA is building a large part of its physical AI strategy around this workflow. Its robotics platform connects simulation, synthetic data, robot training, AI models, computing hardware, and real-world deployment. The company has also released robotics models such as GROOT and Cosmos, related tools designed to help machines learn, reason, and operate in physical environments. This explains why NVIDIA is so interested in robotics. The physical AI revolution could require enormous amounts of computing power. Robots need powerful chips for training, but they also need efficient computers inside the machine. A robot cannot always send every decision to a distant cloud server. Network connections may be slow, unreliable, or unavailable. Many decisions must happen locally. A warehouse robot approaching a worker cannot wait several seconds for a cloud response. An autonomous vehicle cannot lose control because the internet connection disappears. Physical AI must often process sensor data and respond directly on the device. That creates demand for edge computing, efficient AI models, specialized processors, advanced sensors, batteries, motors, and entirely new software platforms. But humanoid robots are receiving the most attention because our world was designed for the human body. Doors, stairs, shelves, tools, vehicles, workstations, and factory equipment were largely created for people. A robot with 2 legs, 2 arms, hands, and a human-like height may be able to work in existing environments without requiring companies to redesign every building. That does not mean every future robot will look human. In many situations, wheels are more efficient than legs. A robotic arm may be better than an entire humanoid body. A drone may be the right machine for inspecting power lines, while a 4-legged robot may be better for dangerous industrial sites. The most useful physical form depends on the task. However, humanoid robots could become valuable in environments where companies need flexible machines capable of performing many different types of work. And this is already moving beyond laboratory demonstrations. Agility Robotics says its Digit humanoid moved more than 100,000 totes during a live commercial logistics deployment. The company has also announced a commercial agreement for Digit robots to support manufacturing, supply chain, and logistics operations at Toyota Motor Manufacturing Canada. Boston Dynamics is transforming Atlas from an experimental research robot into a system designed for industrial work. The company has also partnered with Google DeepMind to combine Atlas hardware with Gemini Robotics foundation models. Figure is developing humanoid robots and its Helix AI system for full body control. The company has reported increasing production of its Figure O3 robots and has continued testing its machines in real industrial environments, including work connected with BMW manufacturing facilities. These examples do not mean that general-purpose humanoid robots are already ready to replace human workers everywhere. They are not. Most physical AI systems still operate within carefully selected environments and limited task categories. A successful demonstration does not automatically mean a robot can perform reliably for thousands of hours. Real-world reliability is one of the biggest remaining challenges. A chatbot can occasionally produce a bad answer, and the result may be inconvenient. A physical AI system can damage property, interrupt production, cause an accident, or injure someone. The acceptable error rate is much lower. Physical AI therefore requires multiple layers of safety. The AI model must understand risks. The control system must limit unsafe movements, the hardware must detect collisions, and the entire machine needs emergency procedures. Safety cannot simply be added at the end. It must be built into the sensors, models, processors, software, mechanical design, testing process, and deployment environment. This is becoming a major focus for the industry. NVIDIA, for example, has introduced a full-stack safety system called Halos for robotics, reflecting the growing need to combine AI capability with functional safety and real-time protection. Autonomous vehicles are another important form of physical AI. A self-driving car must understand roads, traffic lights, pedestrians, cyclists, weather conditions, construction zones, and the unpredictable behavior of other drivers. It must continuously predict what could happen next and select the safest action. Waymo says its autonomous driving system has accumulated nearly 200 million fully autonomous miles and billions of additional miles in simulation. The company is also expanding fully autonomous operations into more cities, showing how physical AI can gradually move from experimental programs into real transportation services. And cars are only one category. Physical AI could transform agriculture through autonomous tractors, crop monitoring drones, and robots that identify weeds or harvest produce. It could transform healthcare through surgical systems, rehabilitation robots, hospital delivery machines, and devices that help elderly or disabled people live more independently. It could transform construction through autonomous equipment, robotic inspection, and machines that operate in dangerous environments. It could transform energy by inspecting pipelines, power plants, offshore platforms, and electrical infrastructure. It could even transform science. Automated laboratories could use robotic systems to prepare experiments, test materials, collect results, and allow AI models to design the next experiment. The economic impact could be massive because physical AI does not only automate information, it can automate physical labor. But this also creates a difficult question. What happens to human jobs? I do not believe the answer will be as simple as saying robots will replace everyone or robots will replace nobody. Some tasks will clearly become automated, especially work that is repetitive, dangerous, physically exhausting, or difficult to staff. At the same time, physical AI will create new jobs in robot maintenance, fleet management, safety testing, simulation, hardware manufacturing, data collection, systems integration, and robotic software. The larger change may be that many jobs become a partnership between humans and machines. A worker may supervise several robots instead of carrying every box manually. A technician may use an autonomous inspection robot instead of entering a dangerous location. A nurse may spend less time transporting supplies and more time working directly with patients. The outcome will depend on how businesses deploy the technology, how quickly workers can learn new skills, and whether productivity gains are shared across society. There are also serious questions about privacy and security. A robot operating inside a home or workplace may collect video, audio maps, and information about human behavior. Who owns that data? Where is it processed? Could the robot be hacked? Could someone take control of its cameras, movements, or decision-making system? As AI gains access to the physical world, cybersecurity becomes physical security. This is why physical AI may require stricter standards than ordinary software. Developers will need secure hardware, encrypted communication, controlled access, clear data policies, continuous monitoring, and reliable ways to stop a machine when something goes wrong. So, how close are we to the physical AI future? I would describe the current period as the transition from impressive prototypes to early commercial deployment. We already have useful autonomous machines in warehouses, factories, roads, hospitals, farms, and industrial sites. But we do not yet have affordable, reliable, general-purpose robots that can enter any home or business and perform almost any physical task. The technology is improving quickly, but the physical world is much harder than the digital world. Progress will depend not only on better AI models, but also on better batteries, cheaper sensors, stronger materials, more reliable motors, improved manufacturing, safer control systems, and massive amounts of real-world testing. The first major wave will probably happen in structured commercial environments. Factories and warehouses offer predictable layouts, repeatable tasks, measurable economic value, and professional maintenance teams. Once robots become reliable there, they can gradually move into less controlled environments. The home may be one of the final and most difficult destinations. Every home is different. Objects are placed randomly. Children and pets move unpredictably. Tasks require common sense, delicate manipulation, and an extremely high level of safety. But once physical AI becomes reliable enough for the home, the impact could be extraordinary. Imagine a machine that can clean, organize, carry groceries, prepare simple meals, help elderly family members, perform basic maintenance, and learn new tasks by watching a demonstration. That would not simply be another electronic device. It could become a new category of personal infrastructure. The last major AI revolution gave machines the ability to generate information. The next revolution will give them the ability to act. AI will no longer be something we only communicate with through a keyboard. It will see the same world we see, move through the same spaces, use the same tools, and increasingly participate in the physical systems that keep society running. The smartphone brought computing into our pockets. Generative AI brought intelligence into our software. Physical AI will bring intelligence into machines. And when intelligence can understand the real world, make decisions, and take physical action, AI stops being just a tool on a screen. It becomes part of the world itself.